Good morning. We have already identified that a capacitor is a way to store electric potential energy in an electric field, and that the capacitance of a capacitor equals the charge stored on the positive plate of the capacitor divided by the positive electric potential difference between the two plates.
Flippin' physics.
The capacitance of a capacitor only depends on the physical properties of the capacitor. For example, the shape of the capacitor and the material used to separate the plates of the capacitor. While there are many shapes of capacitors, we are only going to discuss the simplest capacitor shape, a parallel plate capacitor. The plates of an ideal parallel plate capacitor are considered to be two infinitely large, parallel, oppositely charged plates with equal magnitude charge, which create an ideal uniform electric field between them. Right now, notice that in our illustrations, the plates each have been charged to an equal magnitude charge of capital Q. The electric potential difference between the plates has a magnitude of delta V. The distance between the plates is lowercase d, and there is an electric field between those two plates that is capital E. Now, the capacitance of an ideal parallel plate capacitor equals the lowercase Greek letter epsilon with a subscript of naught times capital A divided by lowercase d, where epsilon naught is the electric permittivity of free space, and it is also called vacuum permittivity. The electric permittivity of free space is a constant which is equal to 8.85 times 10 to the negative 12 coulombs squared over the quantity newtons times meters squared. I'm not really going to talk about the electric permittivity of free space right now because I have an entirely different video dedicated to that. For now, just to know it is a constant in the numerator of the parallel plate capacitor equation. Capital A is the area of one of the plates, not the area of both plates. And lowercase d is the distance between the two plates. This equation assumes there is absolutely nothing between the two plates, not even air. In other words, there is a vacuum between the two plates, hence vacuum permittivity.
But capital A would be infinitely large, right?
What? Why?
He just said that the plates of an ideal parallel plate capacitor are considered to be infinitely large. So the area of the plates, capital A, should be equal to infinity.
The phrase considered to be there means that the width and length of the plates are both so much larger than the distance between the plates that the area of the plates can be considered to be infinitely large.
Okay, sure.
I feel like it would be difficult to keep the two plates separated at a uniform distance with absolutely nothing between the two plates, right?
Yeah.
That is why usually there is an insulating material between the plates of the capacitor. This is both to help separate the two plates, as Billy pointed out, and the insulator increases the capacitance of the capacitor, which allows the capacitor to store charge more easily. The insulating material between the plates of the capacitor is called a dielectric. To illustrate that this parallel plate capacitor now has a dielectric between the two plates, I have added a red rectangle between the two plates in the illustration. Bo, assuming the capacitor is not electrically connected to anything to allow the charges to flow to or from the capacitor is electrically isolated. What changes and what does not change about the capacitor when we add a dielectric?
Sure. The capacitor is electrically isolated such that charges cannot flow to or from the capacitor. That means that the magnitude of the charge, capital Q, on each of the plates will not change. We are assuming the addition of the dielectric does not change the distance between the two plates, right, Mr. P?
That is correct, Bo.
That means that lowercase d does not change. What else?
The magnitude of the electric field decreases.
How do you know that?
From the illustration, without the dielectric. Look at how many electric field lines there are, and then look at how many electric field lines there are with the dielectric. Clearly, the electric field decreases in magnitude with the dielectric.
Yep, you can see that from the illustration.
That is about the worst reasoning I have ever heard of.
Yeah, that is probably true. However, I cannot really show that the magnitude of the electric field here decreases with the addition of a dielectric until we take more time next time to delve further into what the electric permittivity of free space is and what dielectrics are.
Okay.
Bo, please keep going.
Sure. We know from the illustration that the magnitude of the electric field decreases with the addition of the dielectric. We also know the electric field is uniform, so the electric potential difference between the two plates equals the negative of the electric field times the distance between the two plates. Therefore, because we know that the electric field decreases and the distance between the two plates stays the same, the magnitude of the electric potential difference between the two plates also decreases. And because capacitance equals charge over electric potential difference, and the charge stays the same while the magnitude of the electric potential difference decreases, the capacitance of the capacitor increases when the dielectric is added between the two plates.
In other words, assuming that adding a dielectric to an electrically isolated capacitor does not change the distance between the plates, lowercase d, and we know the charge in the positive plate, capital Q, does not change because the capacitor is electrically isolated, the magnitude of the electric field decreases, which decreases the magnitude of the electric potential difference, which increases the capacitance of the capacitor.
That is what I said.
I know, I just said it smoother.
Sure.
Yeah. Okay,
Yeah.
now I could give the equation for the capacitance of a parallel plate capacitor with a dielectric between the two plates. It equals the lowercase Greek letter kappa times the equation for the capacitance of a parallel plate capacitor with a vacuum between its plates, where kappa is the dielectric constant.
That looks a lot like just a lowercase k.
I know it looks a lot like a lowercase k, and the dielectric constant has no units. If the dielectric constant did have units, this equation would result in different units than the equation for capacitance of a parallel plate capacitor with a vacuum between the plates. Some typical dielectric constants for a vacuum, exactly 1, because that's how the electric permittivity of free space is defined, with a dielectric constant of 1. The dielectric constant of dry air at room temperature and atmospheric pressure is 1.00059. For polyethylene, it is somewhere between 2.2 and 2.4. For rubber, it is 3.0. For paper, it is in the range of somewhere between 2 and 4. For silicon at room temperature, it is in the 11 to 12 range.
So all dielectric constants are greater than 1?
Other than for a vacuum.
Sure.
Yes, all dielectric constants are greater than or equal to 1. And let's return for a moment back to something I said near the beginning of this lesson. Billy, could you please read this quote?
The capacitance of a capacitor only depends on the physical properties of the capacitor. For example, the shape of the capacitor and the material used to separate the plates of the capacitor.
Oh, I get it.
Get what?
The capacitance of a parallel plate capacitor is only determined by the dielectric constant of the material between the plates, the area of one of the plates, and the distance between the two plates. Those are all physical properties of the capacitor.
And even though capacitance is defined as the positive values of the charge stored on one plate of the capacitor over the electric potential difference between the plates of the capacitor, the capacitance of a capacitor only depends on physical properties of the capacitor and not on how much charge is stored on one of the plates or the electric potential difference between the plates.
Okay, yeah, that does make sense. And in fact, the capacitance of a capacitor is still there, even if the capacitor has no charge or electric potential difference between the plates. The capacitance of a capacitor simply represents how many coulombs of charge the capacitor could store per volt of electric potential difference. Yeah.
Yeah.
Yep.
Absolutely. Now, clearly I have a lot more for you all to learn about capacitors. However, let's leave all that for another day. Thank you very much for learning with me today. I enjoyed learning with you.